Hello friends, this is Abhishek Agarwal. I am a performance/automation consultant in test, and welcome to my video of what is Big O. So Big O notation is one of the mathematical notations that was invented by Paul Benjamin and Edmund Landau, collectively also called as asymptotic notation. Some people refer to this term as asymptotic and some people refer as Big O. In this video, I will be referring this as Big O as we proceed further. In simple terms, Big O can be used as a unit to define the function's efficiency or the resource utilizations of CPU time, memory, network when the function is executed. This is the first half of the definition, but the definition will be incomplete without the second half or the second point, which is the resource utilization in proportion with the amount of data that this function is processing. So as you can read, how the performance of the function changes in proportion to the size of the data that the function deals with. So these are some basic Big O notations that have been provided by Edmund Landau. O of 1, O of n, O of n square, O of log n, O of n log n. And as we proceed further, I would tell you which notation means what, and I'll also run some small programs which I've already written to show you how these relate to the functions. So O of 1 is when a particular function takes the same amount of time regardless of how big is the data on which the function is being processed. For example, if you want to add an employee to a database which has 1,000 employees already existing in the database, versus if you want to add an employee to a database which has probably 100,000 employees data record already in that database. So the time taken to add that particular employee in the database is going to remain the same regardless of the size of the database. In this presentation over here, as I've mentioned, adding an element to an array or getting the size of the array, both these functions are going to take the same amount of time, memory, everything, if it had to perform on different sizes of arrays. Moving further, O of n. O of n is when the amount of time taken by the function to process increases in proportion with the amount of data being processed. For example, printing all the elements in an array. Linear search algorithm. So let me demonstrate the linear search algorithm over here. It's here. So in linear search algorithm, let me quickly just explain you what this code is doing. I'm having a class file called as Big O notation, and I'm having a constructor as well for this class. And what this function f3, okay, so what this constructor is, what this class file is doing is I'm having some private integer array that I've declared, and this integer array I'm initializing as soon as an object of that array is created, and in that initialization I'm telling what should be the size of that array. I also have a generate random array function that I've created, wherein I'm adding some random numbers to that array, math.random, which generates random numbers from 0 to 1, and then I multiply that by 1,000 so that I can get a number up to 999, and then I'm adding 10 because I want my numbers to be between 10 and 999. So that's what this is doing. I have a basic swap function which is going to swap 2 elements in an array, pretty straightforward. And let me now show you the linear search function. So this is my linear search. So what it is doing is it is just taking a value that needs to be searched, and it is going to search for that value, and whenever it finds that value, it's just going to increase the count. So this is O of n as I've mentioned over here, and let me show this to you by running this algorithm. So we have got 3 different objects that have been initialized, and for all 3 different objects we have created the generated the random array of a particular size, like 10,000, 40,000, 60,000, and I'm going to do test algor search on all the three arrays. Let me increase the size actually, because the linear search is O of n. It's a bit faster. I should see some time in milliseconds over here. And okay, so just I think I did not mention that how I'm calculating the time. So let me quickly just show that to you. Function f3. Okay, it's here. So over here, what I'm doing is, before my program starts getting into the for loop, I'm just taking the system time in milliseconds over here, start time, and as soon as it exits out of the for loop, I'm taking the system time in milliseconds, and I'm just subtracting both the times to give you the array size, and then but obviously the count to give you the total number of times the linear search fetched the count. So now I'm going to run this code to find the value 20 in all the three arrays: test algo 2, test algo, algo 2, and algo 3. So let me run this one. So okay, I accidentally also ran the binary search, which I do not want to run it now. So let me run this quickly again. So as you can see, the total execution time that was taken for the first one was 2 milliseconds, the second one was 2 milliseconds, and the third one was 1 millisecond. Ideally, this would you know, with an array of size 600,000, this should go higher, but you know, this also really depends on how the JVM is being used at that point of time when this function was executed. This is a very small function to give you an example for. So let me change some numbers over here, or let me do one thing over here. Let me execute one by one, and probably that we might get the right. So when I'm executing for 100,000 arrays, it took 3 milliseconds. As you can see, earlier it took 2 milliseconds, and now it took 3 milliseconds. And now when I execute for the second algo, it took 2 milliseconds. Okay, and let me execute for this one, and let me make it like 9. So as you can see, it took like 6 milliseconds. When I changed my size from 100,000 to 900,000, the time has gone from 2 milliseconds or 3 milliseconds to 6 milliseconds. So the time is increasing, but it's not increasing like, you know, exponentially, I would say. So this is what is O of n. So it just increases linearly. Next one is O of n square. So O of n square is when the time taken to process by the function is going to significantly increase with the amount of data that it is dealing with. Now, just to remind you that the big O complexity notations are not only for time, but it's also for network and memory and everything, as we discussed earlier. But in my examples over here, I'm just focusing on time because it's easier to explain, and it's something which I think you'll understand. So over here, O of n square is when the time taken to process by the function will increase significantly with the amount of data that it is processing, and here the time taken is increasing more than O of n. So for example, compare each element of array to every other element of the same array to find duplicates, or bubble sort algorithm. So let me go ahead and show you the bubble sort algorithm over here, which I have already written as well, and let me comment this out. So I think here we should be able to nicely see how how the response time or the processing time increases with the increase in number of size of the data that is being passed for that function. So over here, let me change this array from 100,000 to 10,000, 40,000, and 90,000, because bubble sort just takes a lot of time as compared to linear search. So let me run this one now, and if you want to see the function for bubble sort quickly, function f3, This is what it is. What it is doing is, for every every element I, it is for every element it is comparing itself with all the remaining elements, and if it is less or if it's more than any of the element further, it's just going to replace itself. So this is the swap function over here. So let me run this particular code quickly with the three different array sizes, 10,000, 40,000 and 90,000, and you will see how the processing time changes and varies significantly as it's O of log n, it's n square. So total execution time taken for an array of 10,000 is 992, and the total execution time for an array of 40,000 is 3241 milliseconds, and for the third one is almost above 8 seconds. So as you can see that how the time is exponentially increasing with the increase in size. This particular piece of code is O of n square. So let me move further to O of log n. Now O of log n is when the time taken to process by a function increases minimum as compared to the amount of data that is being processed. It is going to be lesser than O of n square. So for example, binary search. So what we do in binary search is we don't iterate and compare each element of the array with every other element, but we are just going to divide the array into half. Now before I say that, let me also let you know that for a binary search to be performed, the array needs to be in a sorted order already. So you first need to call an array to sort it, and then you call the binary search. So let me show that to you in an example over here as well. So let me have these three bubble sort algorithms run one after the other, and then I'm going to perform the binary search over here. Okay, so it just took a lot of time this time. And if you see the binary search for the same array for which the bubble sort took 429, 4 seconds, 2 seconds and 8 seconds, it just performed in 1 second, 0 second and 0 second. So it's just it is just too fast even to notice the difference between 10,000, 40,000 and 90,000 elements in an array. So moving further, let me tell you O of n log n. O of n log n is considered as most efficient in performance notation out of the ones that I've showed in this presentation. So the amount of time taken to process with the increasing data has a very slight change with the increase in data. So for example, quicksort, it's a divide and conquer algorithm. It picks up an element as pivot and partitions the given array around the picked pivot. Let me quickly show this quicksort as well. As you saw earlier in the earlier example, I showed you that with bubble sort with an array of size 10,000, it took 429 seconds, and we just took the array of sizes 10,000, 40,000 and 90,000. Now with quicksort, if you look at the array size 10,000, and let me uncomment this one. Okay, and I'm going to say 10,000, 40,000 and 60,000. You see, and I'm going to call the quicksort function, and once I call this one, it's going to display the timings for me. So if you see, the same size of arrays that we processed earlier and which took like in time in seconds is getting processed with quicksort in milliseconds. And if you see that the difference as the data size is increasing, the difference is not too high. It's still in milliseconds. So Let me increase this size to 100,000, 400,000 and 600,000. So we are increasing it 10 times than what we used in bubble sort. So you can see it's still in milliseconds, 28, 48 and 117. So with quicksort it's much faster as compared to bubble sort, and the big O notation for this one is O of n log n. Now keep in mind that quicksort also has a worst case of O of log n, I believe, and I'm not sure on that, I believe, but it does have a worst case. What it means is it really depends on the kind of data that is being sent. If an array goes to quicksort which has already been sorted, then it might not perform as good as it's performing now. So that's just a quick note in between. Going further, I will explain you the different rules that we need to apply while finding notations of a particular function. So for example, if a particular function has two different steps, and these two different steps have two different arrays. For example, the first step is finding a minimum value in the first array, and the second step, B, is finding a minimum value in second array. So in that case, the big O notation would be O of A plus B, because you see there are two different set of arrays, that there are two different data types. So we cannot just have like O of A plus A or O of n plus n, or O of 2n, anything like that. So that's O of A plus B. The next rule would be drop constants. For example, a function is having two steps, and step A is finding minimum in first array, and step B is finding minimum value in first array again. So ideally the maximum value in first array again. So ideally you would write a function wherein you iterate through the array only one time, and then you find the minimum and maximum at the same time. But let's assume that there is a function which is written which iterates two times, once in step A to find a minimum value and once in step B to find a maximum value. In that case, the big O would not be O of n plus n or O of 2n, it would just be O of n, because it's still just only one array that we are dealing with, and the time that is going to increase, it's going to increase linearly. We have to compare to the time of that function what was earlier. The next one would be different inputs is equal to different variables, as mentioned earlier. It's the same thing. Over here, this example, we are having compare array, wherein we are comparing two different arrays. So for every element in the first array, we are comparing with every element in the second array. Over here, as soon as you see this one would say that this is O of n square, because it's just similar to bubble sort, what we saw earlier. But this is not O of n square, because these are two different arrays. So it would be O of A into O of B, and since it's nested, it is a multiplication over here. If these would be in two different steps, as explained earlier, it would have been a plus sign over here, O of A plus B. So this is the third rule that we need to apply when defining the big O notations for a function. The fourth one is drop non-dominant values. For example, 45n cube plus 45n square plus 45n plus 10 is going to be, if n is 1, then this would be 145. So going further, if this n increases, if n is 2, then what happens? If n is 2, this value would be 640, and if you look at this value 640, if you just remove the first constant, the last number over here 10, which is the constant, it really doesn't matter. It would be 630, which really doesn't matter. And or even if you remove the number 45 from here, it's going to still be 595, which is almost close to the 640 number. So it really doesn't matter if you remove 45 or 10 of the last two constants. Sorry. So and the last example, as the n increases further, when n is equal to 10, for example, so 45n raised to 10, so 10 raised to 10 cube, which is 45,000, plus 10 square, which is 100 into 45, which is 4500, plus 45 plus 10, which is 49,555. Over here, if you see, even if I remove 4,500, 45 and 10, even if I remove all these three terms, I would still get 45,000. So essentially, if I'm having 45 n cube, then I don't need to still have my notations include n square and n and a constant over here, because the n cube itself is so high that the remaining numbers are low and those could be ignored. So that's why this rule states drop non-dominant values. So that is pretty much. If you have any questions, comments, feel free to put those on the in the comment section below, and I will try my best to reply to those. Thank you for watching. See you again.